Here I'm gonna cover the concept map for nuclear physics, which is the chapter 10 of the OpenStax textbook. And when we're looking at the nuclear physics, we look at the atomic nucleus microscopically. And when we're looking at the atomic nucleus, it contains nucleons, and we could classify nucleons into two types of subatomic particle called protons and neutrons. The protons tell us what the atomic number is, like which element are we referring to, and the neutrons tells us the neutron number, which when we're combining with the number of protons, that gives us the mass number. So when we're looking at the nuclear size, we have this equation that tells us for certain mass number of the atom we have, then it should have certain radius of the whole nucleus. And one interesting phenomena we're looking at for atomic nucleus is something called mass defect and binding energy. What it's saying is that the total mass of the whole nucleus is actually different if we're separating the nucleus from protons and neutrons. So the sum of the mass of the protons and neutrons is actually different from the mass of the nucleus itself. And the difference is called the mass defect. And if we're converting mass defect to binding energy, we're looking at E equals to mc squared. And I talked this a little bit in the problem too. So after we look at the mass defect, we're saying that this energy, this binding energy, we're saying that this binding energy, it emits via radiation, and that energy radiation is something that happens inside nuclear radioactivity. And the nuclear radioactivity, we're saying that for every emission of the radiation, the emission of energy is basically talking about a decay of an atom. So the atom would lose some mass by forming another element with lower atomic mass, probably the emission of energy with some release of neutrons, or breaking one atom into two smaller atoms. And that happens when the nuclear we're talking about is having an atomic number that is greater than 82, or some isotopes with atomic number smaller than 83. Then we could look at the radioactive decay and the nuclear reactions behind. Oh, sorry, I skipped the radioactive decay. The radioactive decay, there's the law, the radioactive rate law is the rate law. The name of the law is it's something called the radioactive decay law, and that tells us how many number of nuclei we have after some time. And I'm gonna look at that a little bit with the problem later. But right now, we'll move on to the nuclear reactions, which is basically about the radioactive decay. And we classify the nuclear reactions into three different reactions. The first one is called the alpha decay. The alpha decay focuses on this helium, the alpha particle. We're saying that one atom would break into another smaller atom with a release of a helium atom. And we're calling the helium atom in an alpha particle. And the atom that has a larger atomic number as the parent nucleus, the atom with a smaller atomic number as the daughter nucleus. And to give an example to illustrate what's happening is when we're looking at uranium-238 uranium with 92 atomic number. This would first break to one helium, and then this 238 with -4, which gives us 234. 92 minus 2 gives us 90, and for 90, when its atomic number is 90, we're looking at TH. So this is just an example of what radioactive decay looks like, the nuclear reaction behind. And the energy emitted is that when we're looking at the difference in mass of this nucleus and this whole thing, the difference in mass is the energy emitted throughout the reactions. And for the beta decay, this is the definition of the beta decay, is that it releases 1 electrons. And this thing is just to make the equation, it's just to balance the equation with some angular momentum inside. And yeah, so for beta decay, the atom would change to another atom by losing 1 proton, and sorry, it's not losing one, it's losing 1 atomic number and 1 electron as well. For gamma decay, we're saying that, oh, this atom and this atom is the same. So what happens here is that it just releases some gamma radiation. So the atom does not change, but it emits gamma radiation. So all these nuclear reactions is actually an introduction to nuclear fission and nuclear fusion, which is the core part of nuclear physics. When we're looking at nuclear fission, we're saying that the splitting of a nucleus, so some fragmentations of an atom, like uranium. So here's an example of what nuclear fission looks like. So we have the uranium, and then when 1 neutron hits the uranium, it's gonna break apart. It's gonna break to form 2 smaller atoms because as the atomic number goes up, the neutrons would essentially, the difference between the neutrons and the protons would essentially be larger. So there should be some neutrons giving out. And this Q is basically saying that there's heat and energy releasing throughout these reactions. So as we can see, that the uranium could break up in different forms. It could break up to form barium and kryptonium, or it could break up to form this thing and this thing, this thing and this thing, like different combinations of it. But the essential part is that this is actually inducing some something called chain reactions. The focus we're looking on is this neutrons. And this neutron would essentially come back to replace this neutrons. So a better illustration is looking at this diagram. When a neutron hits the uranium would break into 2 smaller atoms with some energy. And well, we could use this energy in empowering the nuclear energy. But what's more interesting is that it forms 3 neutrons, extra neutrons. And these 3 extra neutrons would attack another 3 atoms of uranium, and these 3 uranium would break apart. Maybe this time this uranium would not form krypton and barium. Maybe this time the uranium would form Xe and Sr. And maybe this time this uranium would break into forming Sn and Mo. So on and so on. So every time that the uranium is being fragmented into 2 different atoms, it also forms the neutrons, and that neutron would then become the reactant to form another product. So this is called the chain reactions. When we're looking at nuclear fusion, we're not looking at the fragmentation of 1 atom. We're looking at the combination, the fusion of 2 atoms, the 2 atom nuclei to 1 heavier nuclei with some release of energy. So we see the energy here again. And in this case, we're saying that we look at one example is from the sun. How the sun releases energy is that some scientists they say like it's via the nuclear fusion. So 2 hydrogen atoms would form a heavier nuclei. And same thing here, it's gonna form a heavier nuclei, we could see. And when it combines to when two atoms combines to form 1 heavier nuclei, it's gonna release some energy. And if we're actually looking at the sum of it, so the 3 equations would combine to give us this equation. Would form, for H11 would form form a helium atom here plus 2 electrons plus some gamma radiation, and we're using this to balance off the equation, and some heat. And this is something called the nuclear fusion. And that concludes the whole concept map for this unit, chapter 10. Thank you.